slides here. Well, we're very pleased to have this evening for the distinguished lecturer, Michael Berry. Professor Berry's been at Bristol since 1965.
More than twice as long as I haven't.
Twice as long, yes. And where he's currently the Emeritus Professor of Physics. His list of awards and prizes, it has at least 28 entries. I don't think I'll read them all. The classics are the Dirac Medal, the Lorentz Medal, the Polya Prize, and the Wolf Prize. His website's great. It has a picture of the Silver Dragon, and it's even better if it's what you're going to be talking on today, I think. And this talk is about chasing the dragon, tidal bores in the UK and elsewhere.
Thank you. Slightly different title now. I'm very pleased to be giving this talk to cognoscenti, by which I mean people who know about some aspects of water waves much more than I do. Some of you, at least one of you, has heard me speak on this subject before, so I want to say that the technical part of the talk is completely different now, and that's because although what I'll present, the main conclusion is the same as before, an important feature of the propagation of this particular kind of wave was something I had missed, and it was brought to my attention by Karima Kusnutdinova, and I'm very pleased that she's here so that I can acknowledge her directly. Now, it's an anti-Einstein talk. You know, I'm not interested in this phenomenon or that phenomenon. I want to know God's thoughts. The rest is mere detail. Now, this is about one particular natural phenomenon. And he wasn't so uninterested as he pretended. I mean, he wrote a paper on the meandering of rivers, and he co-invented a new type of refrigerator. It wasn't really quite as purist as he pretended. Now, but on the other hand, there's Robert Hooke. The truth is, the science of nature has been already too long made a work of the brain and the fancy. It's now high time that it should return to the plainness and soundness of observations on material and obvious things. Well, that's also not quite right, because you really do need theory if you want to understand something, and it's not obvious, this phenomenon I'm going to describe. So this is a kind of intellectual sandwich. The bread is non-technical, 2 bits, the beginning and end, but the filling is the technical part, which I've completely rewritten. So it's a wave travelling up. How many of you have seen tidal bores? Okay, so some of you have. Good, but not many. It's a wave that travels upriver. This is one in Brazil, and the tide comes in and meets the water flowing down and downstream flow of the river, and these waves develop. I'm going to speak about undulations bores, with where you get these characteristic waves, and here's one near Bristol, near where I live. You can see it about 20 days or nights each year. It depends on astronomical alignment, so I'll say that in a minute. Here's another one, and you can see the waves persist even though when there's lots of windy or turbulence or decorating them. Very, very quite gentle, you see, these waves, although they look much more dramatic than they actually are. Here's a wonderful little movie from Bruce Anderson, which is Drone. A drone is perfect for seeing the bore. I'm going to describe these waves in the middle here, because it's everything about a natural phenomenon is complicated, and near the shore you usually get some turbulence, but I'm going to discuss the waves in the middle, and you see a good collection of them here. Oh, this is on the River Nith. I'd never heard of the River Nith. It's in Dumfries in southwest Scotland. And it's a pretty little bore. The river's quite narrow, and there it is. And here again you see very gentle waves. They look, as I say, much more dramatic when you see them from above. Mine, okay, I say mine, on the River Severn, well, here it is. There's Bristol, and then there's Gloucester. So the bore happens upstream near to Gloucester. Let's zoom in, and this is 2 kilometres, and around this region up to Gloucester, and then Maysmore, where it ends because there's a weir which stops it. It used to go all the way up to Worcester, even farther, but it goes for sort of 50 or kilometres or so along. It starts downstream of here. Good. Now, just elementary things. There's one particular point that amuses me, and it's worth saying. Of course, there are 2 tides every day, and sometimes a year you can see the bore twice a day. And people are often puzzled why there are 2 tides a day, because they imagine the moon pulling the Earth's water, and you expect the water to accumulate on the side of the moon, so the Earth slides around and you see it once a day. And there's something very amusing about the fact why this is not true. You see, the water on the moon side is more strongly attracted than the water on the solid Earth. And the water on the far side is less attracted than the water on the solid Earth. So, and that gives rise to these 2 bulges. Well, why does it? Because if you had the Earth fixed in a cosmic vice, you would have a bulge on the side pointing towards the moon. But it isn't. The Earth is falling freely in a way determined by the force on its solid mass. And what is that? Well, it's actually Einstein's principle of equivalence, which I saw anticipated 1,000 years before in the Arabian Nights. So I'd like to read you that. It's when Sinbad is taken up by it. The bird which rose and rose until I thought it was about to touch the vault of heaven. Then suddenly it dropped so swiftly I could not feel my own weight. And that's exactly Einstein's principle of equivalence 1,000 years before. So you get these 2 bulges. Now, so that means, of course, it's the difference force between the water and the solid Earth. So it's the gradient of the tidal force, the 2 bulges, and the tide raising force is 1r cubed, not 1r squared. And that's why it's the moon that causes it, because that's greater for the moon than for the sun. If it weren't so, 1r squared, of course, we go around the moon, we don't go around the sun, we don't go around the moon except for a little wobble. But the sun tide isn't negligible. It's about half as big as the moon tide. So depending on astronomical alignments, and there are a number of them, the tide and the bore that I'm going to describe can be of very different strengths. Now, the other point is, of course, that as the water goes upriver, a wave develops, and there's a nice way of describing, at least to non-technical people, though you might wince with horror, why it is that waves steepen and then eventually break, although that doesn't always happen with the bore, which is this, that the speed of waves on water is, roughly speaking, root gh. That's the limiting speed. And gravity waves, I mean. But of course, in the crest, d is greater than in the trough. So loosely speaking, the crests travel faster than the troughs, and eventually they can overtake, and hence you get this steepening. Now, if you stretch out this 50 kilometers or so where you get the bore, normally the river goes downstream. It falls about 10 meters. But when the bore comes, and I've exaggerated this height enormously, when the tide comes in, this is a static picture. You see, the bore is the beginning of the tide, and then there's high tide, and then farther down the tide is ebbing. Now, one of the most dramatic things when you see the bore is that the river reverses. And so what the river is doing, it's flowing upstream here, but downhill. So nothing paradoxical, but just it just needs to be thought about. So that's the structure that we're speaking about. And I'm going to talk about undular bores, this particular kind, not the turbulent bores that I'll also show one or two a little bit later. So here we are again, and here we are again. You know, tens of meters between the first two maxima. And here's a still from from Bruce Anderson's video that I showed you. Now, what I'm going to present is a minimal model for the shape of an undular bore. This is a very useful term. I dislike the term toy model that you sometimes see, because that has an aroma of triviality. And often they're not. I mean, in condensed matter physics, I mean, the phase transition, the Ising model is often said it's a toy model. It's kind of disparaging. I prefer minimum model. It's a term used by Nigel Goldenfeld. It most economically caricatures the essential physics. And that's what I am going to present to you. And that's actually very appropriate for a natural phenomenon, because no mathematical theory of water waves is going to capture, for example, the different material that's on the bottom, whether it can move or whether it can't move, so you won't know the exact boundary conditions, the fact that the river is not straight, the fact that the depth varies, the fact that near the shore the river is shallower than in the middle. I mean, no theory is going to capture all of that, which on the river, as I said, it's not straight, but in fact its width also changes as you go upstream, so you're never going to capture all of that. So a minimum model is appropriate, but the main characteristic of the minimum model that I'm going to present is that it's linear. Now, I know that many water waves are non-linear. I mean, they all are to some extent, but I hope I will convince you that the essential features of what you've seen are described by a linear model, but it has to be the right linear model. Okay, so here's the geometry seen at an instant from a fixed point on the shore, the land-based frame. So upstream, the river is flowing with positive in the x direction velocity. The tide comes in, water's flowing with a negative x velocity, and so is the structure that we want to describe. But it's much nicer to look in a frame moving with this structure. So here it is. As I said, the river usually reverses as the bore arrives, so the river is flowing upstream here. But it's best to change with the frame of reference moving with the bore. Now, this is an approximation, because actually the shape, in a way I'll describe, does change as you move upstream, but slightly. So looking instantaneously here and looking with this moving, it's an adiabatic approximation of the type used, well, for example, the whole of theoretical chemistry, for example, you say that the electrons solve their Schrödinger equations so quickly before the nuclei have time to move. It's an approximation, but it works very well, and that's what I'm going to present here. So this is a little anticipation of later. But anyway, this frame moving with the bore. There it is. And we want to understand various things. We want to understand the shape, the wavelength, if you like, between the first two maxima, the slope at the front, and so on. And in particular, this depth d of x and t. But in this frame, these velocities are downstream, so positive towards positive x. Now, as I say, we want to calculate the profile. Now, a little preliminary, which is not part of my main contribution, there is standard hydraulic jump theory. If you apply conservation of water and Newton's law to a volume of water, including the bore, okay, then this connects the downflowing river speed and depth to the incoming tide speed and depth in terms of one parameter, which is going to be very important in everything that follows. It's the depth of the where the tide is coming in, D1, and D0, the smaller depth of the downstream flowing water. And of course, if there's a bore, this ratio is greater than 1. Now, rules of thumb, which I haven't really confirmed, and I don't know how to, but which I've read, are that you get an undular bore, which I'm going to be thinking about, considering if R is less than 1.5, and a turbulent bore if it's greater. So I'm going to consider R close to 1, which it is in the cases I've seen. I've seen 6 tidal bores around the world, and some of them are turbulent, but most of them are undular. Now, so hydraulic jump theory, conservation of mass and momentum, and these are the relations. It's an exercise, and I won't go through it. It's known. So, but I want to draw attention to a feature of it, based on the fact that the maximum speed that water on depth d can travel, which we'll get to soon, is root g times d. Now, it's this, that upstream, that's ahead of the bore, the flow speed is faster than the maximum wave speed. So waves can't travel upstream away from the bore. They can travel into the bore, but not upstream. Downstream, that's behind the bore, the speed is slower, so waves can travel both ways, and they do. So the front of the bore is a horizon. That means it separates regions where waves can and can't travel upstream. And this is the basis of an analogy with horizons in relativity. I don't want to press that too much, but I just want to describe it a little bit. The common feature is you've got waves associated with horizons. And it's a white hole, actually, because upstream, away from the bore, is into the hole where waves can't travel, but they can travel into the front, that is, into the horizon and out of the hole. So it's like a white hole. And, oops, excuse me. Yeah. So that's a nice connection worth making in this fashionable world of connecting different areas of mundane physics like tidal bores with relativity and horizons. But I want to describe the undulations. That's the main thrust of this bit of theory. And I'm going to do it with linear waves. And linear waves, frequency is a function of wave number. For long waves on shallow water, which you probably all know, the square root of gk times the hyperbolic tangent of hk, waves of wave number k. This is the frequency. Now, important feature, the derivative is the group velocity, which has a maximum speed. Amusingly, of course, if you have surface tension and the waves are small enough, it's a minimum, but which has different physics associated with it. But here it's a maximum, and here it is. It's the long waves that travel fastest. Now, this is for waves on water that's not flowing. Now, in the bore frame, relative to the downflowing water with speed v, for waves advancing upstream in the land frame, you have to, there are many ways to see this. One is use Doppler theory. The other way is from Hamiltonian theory in moving media, different ways. And this is a Hamiltonian in physics. It's frequency, which is like energy, as a function of k, which is like momentum. But here it is, and the sign is because of the way that the waves are flowing. So that's in our fixed, with the Bohr frame, that's the dispersion relation. Now, what do you want to take for V? Well, it actually doesn't matter. It doesn't affect the theory much in this regime, but I'm going to take D0, which is the depth of the water, square root of G times the depth of the water downflowing before the bore comes. Now, the bore will be created as a superposition of plane waves. That's what linear theory does. So, but it's a rather unusual superposition. So let's see. Much nicer to scale to dimensionless variables. Measure distances in terms of the depth and correspondingly the wave number, but measure times. Well, if you transform, it's essentially time since the bore was created divided by the depth. Now, this appears naturally. And here's the point, it's a very large number. If you have a bore that's travelled 10 kilometres from where it begins, a river of depth 2 metres, which is common, T is 5,000. So this is going to be a very large number. That's going to be very important in what follows. And then, of course, you scale the bore profile. If it's the upstream depth plus the difference times this scaling function eta. So at minus infinity, before the bore comes, it is 0, and it's 1 downstream once the tide has come in. So this cleans things up. So here it is again. It's the same formula. Now here's a superposition. You superpose waves of wave number k with some prefactor. Now this prefactor has to be chosen to satisfy these boundary conditions. And the way you do that is this has to have a pole with residue 1 at k equals 0, and the contour has to be below the real axis. You just think for a couple of minutes and that becomes sort of obvious. So I'm writing that g of k is the pole times some denominator which is 1 at 0. That's all, and it actually gets smaller as you go farther away. Now, so here it is, when you can convert that to a real integral, and this is the profile. Now, what's this f of k? It represents the initial shape of the bore, and here's a crucial thing: it gets forgotten as the bore propagates. There's a beautiful universality in this theory, and that'll be a consequence of t being so big. But let's keep it for the time being. I'll illustrate that, not perfectly, but to some extent with a little exact numerical calculation. So I've taken t as 100, which is actually not that big, you'll see. And f of k is 1. And there's all this junk at the beginning. This corresponds to a sharp step at the beginning. And you're not interested in what happens here. It's what happens much later, much near the front that matters. And here I'm taking f as 1 plus k squared. It's a little trigonometric formula that takes you which describes the initial step. And they're not exactly the same, but they will become so if I would go to a larger value of t. But you see the point. This is a smoother step. Good. So the pole contributes a half if x is greater than 0, and a saddle in this integral represents the oscillations. So let's have a look at the saddle. Well, the saddle is that x over t is 1 minus the group velocity. And that equation determines a k. I've defined x over t as u. And this is something that happens all over wave physics. It's a very familiar, Lord Kelvin identified it long ago. The wave number of the local oscillations near where and when you are is that of the monochromatic wave that would travel to x in time t with the group velocity. So that's the perfectly standard result. And here it is. Here's 1 minus the group velocity, and here's k, and here's x over t. So this tells you what the local oscillation is going to be, but it doesn't work near the front, which is exactly what we're interested in. So I can show you how this works. When you go through the calculation, it's this stationary phase plus the downstream. There's an explicit formula, and here it is. And you see, it describes the oscillations beautifully, but of course it fails near the origin. It goes to 0 because that's a consequence of the fact that that we've got these boundary conditions. We have the pole. It's a little bit different from the usual situation where it would diverge at a caustic. You can think of the front, I'd like to think of it, as a caustic of the rays of the water waves in this situation. It's a precise description, but the singularity is a bit different. But okay, now to do better, we can do enormously better by using the technique of uniform approximation. So we'll be able to evaluate that integral everywhere. And the way to do it is the first thing you do is you write the integral as an integral, you can eliminate the pole. That's a lot cleaner, and then this integral will be done at the end. This integral up to from minus infinity to x over t. This gets rid of the pole, and you then have an integral with just this f of k, which isn't a singularity in the denominator. And you transform to a new variable. This is Chester, Friedman, and Ursel, 1950s, beautiful technique that they invented. You transform to a new variable with the same topology, the same qualitative behavior. And it's cubic, actually, as you actually can see if you think for a moment about the dispersion relation. And so it's linear and cubic. Now, what's this psi? You identify it by demanding that this transformation is one-to-one. It's smooth and single-valued. And that means you have to fix it. This side with Q has its saddle point, and this side with K has its saddle point, and they have to correspond. And it's a little calculation. You get this psi of U and T. U is the new integration variable you got when you got rid of the pole. And here it is. It's a 2/3 power of something well defined, which, by the way, becomes negative if you're upstream of the Boar. But then the two saddle points are complex, but this is still real. It's negative, and well, so then you apply the transformation, and the Q. And Q goes from minus infinity to infinity. It says you can easily confirm that. And you've got this little Jacobian. It's still exact. The approximation is to say that this prefactor, you approximate by putting the Q corresponding to the saddle point, whether that's real or complex. Of course, there are corrections. I mean, Chris Howells and I have done this to death. I mean, in general, in Chester, Friedman, and Ursel, there's a formalism for the corrections, but to actually implement it is quite complicated, but you can do it. And you, even in the spirit of the other meeting to this one, the asymptotics meeting, you can go to all orders, you can see the high orders. Don't need any of that. Lowest order is enough, as you'll see. So here it is. Here's the uniform approximation. Here's this integral we introduced, but there it is, explicit, and it's an Airy function because that's what the cubic integral is. So it's an integral of an Airy function, and I want to show you how good it is. As I said, the appearance of an Airy function is unsurprising because a Bohr front is acoustic and two water waves coalesce. Exactly the same happens in tsunami theory, where when after the tsunami has been created and before it reaches the shore, which are two important places, but when it's traveling across the ocean, it's essentially linear. I mean, you've got depth of kilometers and the wave is very gentle. And the tsunami is an Airy function whose amplitude you can accurately represent by this Airy function, stretched appropriately. Even for t equals 20, it's pretty accurate. This is f of k equals 1. F of k is, this is a mistake. It's not -1, it's 1 plus k squared, excuse me. It doesn't matter. So, near the beginning, these are different, but here you see they become similar. But the uniform approximation, which is the dotted line, and the red is the exact integral, applies, is certainly accurate enough for any description of a natural phenomenon. Don't forget, this is the minimal model. Okay, so now the emergence of the universal profile. It's when t is very large, the oscillations are dominated by small k. And you can replace small k by the simplest dispersion, often used, many of you will be familiar. This is a cubic function, it's k cubed, and you neglect the rest. And that's because the saddle point moves closer and closer to k equals 0 as t becomes larger and larger. So then you get this wonderful universal Airy function profile. And it's the integral of an Airy function. And here's x, where you are, and here's t, when you are. And it's this slow expansion that I missed, which Karima insisted on, and she's right. And there's something else. I'll come to that in a little while. Just to see how good that is, that's what would be called in the old language of asymptotic a transitional approximation, valid near the front. But when T's 100, it describes the first couple of oscillations, then it fails. Uniform approximation does it perfectly, but we don't need that. When T is 5,000, there you see it just begins to fail after half a dozen oscillations. And so that is the theory that I'm presenting to you, which I'll discuss the consequences of in a moment. Now, here's an alternative demonstration of forgetting. Taking f, which is the denominator, as this Gaussian, the reciprocal is a Gaussian, which corresponds to an error function initial step. Now, completely different theory. You can get this from the KdV equation. If you linearize it here, because we're talking about slow, gentle bores, and there's an exact solution. It's in the literature, I think in a slightly different form. And here it is. Again, it's the integral of an Airy function, but there are these factors which vanish when T is asymptotically large. So that's a universal profile emerging differently found. And this is literature that Karima drew my attention to. Just to make a comment, KdV is both more general and less general than the theory I've described. It's more general, of course, it includes nonlinearity. It's less general because it makes this cubic approximation to the dispersion relation, whereas with the uniform approximation, you consider the dispersion relation exactly. So, take your pick. Now, so this is the Hoogly Boar function. There it is. Now, I'm going to make another comment, sorry, which I forgot to make. Of course, we're dealing with a natural phenomenon. And a common way to understand minimal models is by a controlled experiment. And there are a number of papers where there are experiments which are controlled and which can compare with various theories. But none of them involve this enormous values of T, where I'm claiming the universal profile emerges. And so I'm not disparaging those numerics. I'm just saying that I'm not even looking at them because they're not in the regime that natural bores correspond to. Okay, so this is the structure. Now, implications of the profile. The first thing, this expansion. Well, here's a map. The bore begins near a place called Or, okay? And people commonly see it at Stonebench and upstream. From Or to Stonebench is 24 kilometres, and the bore takes 1 3/4 hours to get there. From Or to Maysmore, which is where the bore dies, it is 32 kilometres, and it takes 2 1/4 hours to get there. Now, this time difference, T to the 1/3, tells you that the expansion is about 7%, and you don't really notice that. So although the expansion is a genuine feature, over the regime of the where you see the bore, it isn't that important. I mean, it's there, and I'm happy to include it, but it's not very significant. The depth at the front of the bore, well, this eta is 1/3, so basically the depth where x equals 0, that's the inflection point not the inflection point, it's just the 0 of the Airy function whose integral you're taking, it's not the inflection, is about 1/3 of the way up. Okay. Now the slope at the front of the bore, you calculate that, tan theta, and it involves the Airy function at 0, that's where I'm calculating the slope, and it's this radius, this depth ratio minus 1, which is a small thing, divided by T to the 1/3, so the bore gets gentler. Actually, at the inflection point, slightly higher up, it's about 1.5 larger, but if you put some simple numbers in, about a few thousand for T, and for the depth ratio about 1.1 or 1.2, this is a few degrees, which corresponds to what you see. You see, I mean, people think about the Boros as a wall of water. It isn't, not these undulations. They're actually rather gentle, and so a few degrees. Gets gentler as it propagates. Now, what I'm calling the wavelength, the distance between the first two crests, well, that's you can calculate that. It's details don't matter, but it's the depth upstream times t to the 1/3, so it gets bigger and bigger as the bore goes upstream. As I said, it expands. And one, by the way, you put some numbers in, and these are tens of meters, which again is about what you see. You compare with those surface, and tens of meters of the wavelength. The amplitude, the height difference between the first crest and the first trough is the depth times this ratio minus 1. Again, that's quite small, of course it is. We're talking about linear theory, but this is that's how it works, that amplitude. The steepness, which is the ratio of this height difference divided by half a wavelength, is again, it's about a comparable angle to the slope here. The constant is slightly different, but again, it's r minus 1, t to the minus 1/3. This is a speculation now. I'm not really sure about this, but it's worth presenting. Assuming, you know, hydraulic jump theory doesn't conserve energy. And there's a theory, a number of people have written about it, that the energy loss is mainly due not to viscosity, but to waves that take away the energy. And if you use, in Lamb, you can find the energy loss due to waves traveling with for a monochromatic wave. We don't have a monochromatic wave, but if you have one of wave number k, then this is the energy balance equation. And k is actually small for the bores we're interested in. But what do we take for k? Well, we don't really know, but roughly speaking, you can choose it as the depth because of the scaling, and it corresponds to the wavelength I've described, the distance between the first two crests. And if you do that, go through all the algebra that we had before, you get this interesting relation that the wavelength divided by the depth is inverse square root of this depth ratio minus 1, which tells you that the depth ratio minus 1 is linked to the time. It changes, and it's 1 over time to the 1/3. So again, the depth ratio decreases slightly as you go higher up. I'm not terribly confident about this, but still, I wanted to just present it. It's not really part of that theory that I've described. As I described it, the large T and the depth ratio are independent parameters, but there's this speculation that they're linked. Very good. Well, you can't really compare, but I've just taken a still from Bruce Anderson and the integral of an Airy function. Okay, there it is. Right. So it's a white hole horizon, Airy function. You know, it's worth emphasizing the ubiquitousness of Airy functions, because it describes, as Airy indeed knew in 1838, it describes wave near smooth caustics. Now, of course, what I presented is where you stretch it so that it uniformly works far away as well, but still, that's the basis. Now, the commonest caustic is a rainbow, the caustic of the rays emerging from a raindrop. And inside the rainbow, two rays emerge in every direction. They interfere with each other, and that's the basis of the interference fringes that you can see if they're not blurred out by what we in physics now call decoherence, although Thomas Young understood the qualitative essence of it. You know, he when he wrote his paper with his two-slit experiment, he was bitterly criticised, really very nastily criticised by people who said, well, if this guy is claiming that light is a wave, on the evidence of these interferences, why don't we see them all the time? Well, the answer is decoherence. He didn't use that term, but he understood very well and described why you don't. If the raindrops are nearly all the same size, then not too big, so the fringes are not too small and blurred out by the finite width of the sun's disk, then you see fringes. This is the best I've seen. You know, behind a swimming duck or a moving boat, the V shape is a caustic of the rays of the water waves. This is deep water, not shallow water. And across the caustic, you get these Airy function fringes. Fritz Ursel, soon after Friedman, Ursel, the uniform approximation paper, Chapman, Ursel, and Friedman, he wrote a paper in which he explained this Kelvin's ship wave, which is an integral, as a uniform approximation with the Airy function. I put this on my website because when Chris Howes and I wrote our chapter in the Digital Library of Mathematical Functions about integrals with coalescing saddles, we talked about uniform approximations, and we gave this example. And somebody wrote to me from New Zealand to say that they were going to use this pattern to simulate the wakes of ships in Google Earth. I don't think it's happened yet, but it was kind of unexpected thing. Anyway, here we are. The arc sign on third, it's because the dispersion relation is root GK for these, they're essentially short waves on deep water. I mean, short waves on shallow water, not long waves. I want to make a point. If you're in a small boat here, let's say, and a big ship passes by, eventually this V will reach you. Twice as long it takes as you think, because you look at the waves, but the group velocity is only half the phase velocity. But still it will reach you. And in your little boat, we've all experienced this, you rock up and down, and then you're feeling in your body the oscillations of the Airy function in the same way as when you look at a rainbow under these appropriate conditions, you see the fringes, you're seeing with your eyes the Airy function hugely magnified. So, you know, it's a very direct, humanly observable thing. Okay, now, end of technical aspect, got some time. Every year I buy the tide tables, River Severn, and the tide tables give the tide heights at every day of the year at different places on the Severn estuary, the Bristol Channel. The highest is Sharpness, because above Sharpness you've got the canal which links Sharpness and Gloucester to protect shipping from the Boar and from the high tides that you get there. There are a number of accidents. There's actually a nice, if you walk near Sharpness, there's a graveyard. You can go down of the rotting hulks of 10 or 20 or so ships that have come to grief there. Well, you choose the day and you look at Sharpness, here it is, and when the high tide at Sharpness is higher than 9 meters, and here are some 3 cases when that's true, I missed one in the morning there, then you'll see a boar upstream. How big it is, you can't quite predict, because it depends on how much water is in the river already, and it predicts, and also what winds in the Atlantic. So it's not like an eclipse that you predict actually to the second, but this is this tells you that there will be a boar or not. There's this lovely book by Anthony Collas. He's a French surfer who travels the world surfing tidal boars. He's written a couple of books. Le Mascaret is the French, and in there he repeats for the Severn Boar, the times when the Severn Boar passes different places relative to the time of high tide at Sharpness, which is in the tide table. So every year I buy the tide tables, I go through and make a list of when there are going to be boars and when you see them. So, for example, if you're near the beginning of the boar arrives before the high tide at Sharpness, and then farther upstream it arrives after, and you can predict to within 15, 20 minutes or so when the boar will come. Okay. Now, different parts of the world. The Pororoca near Belém, it's on the on tributary of the Amazon. Well, here it is, and there are some rather dramatic. Some parts it is turbulent. There is a wall of water in some particular places there, and in India on the Hoogly, that's a distributary of the Ganges that goes through Calcutta. So here's the Hoogly going up from Calcutta down, and the Boar is in this region. When I saw it, it wasn't very good. I mean, I think I was misadvised about when and where to see it. It doesn't matter. I happened to be for a different reason in Calcutta. But here it is, a turbulent Boar. Here it is again. And I want to show you this video that I found online. Unfortunately, you don't see the waves in midstream, you see the turbulence. It's worth seeing. I don't understand Bengali, so I can't understand what they're saying. But lots of somewhat fanciful pictures of the Boar, including that one. But when I saw it, I mean, it was really tiny. Nevertheless, the boats were in the centre of the river, not by the edge. They were moved, and you saw them twist a little bit as the Boar came by. We were on the wrong side of the gate. It looks more powerful on the other side from where we were. It's quite a wide river there. I want to read you something. The Boar commences at Hoogly Point, the place where the river first contracts itself, and is appreciable above Hoogly town. So quick is its motion that it hardly employs 4 hours in travelling from one to the other, the distance nearly 70 miles. At Calcutta, it sometimes occasions an instantaneous rise of 6 feet. And both here and at every other point of its track, the boats on its approach immediately quit the shore and make for safety in the middle of the river. In the channels between the islands and the mouth of the Meghna, the height of the Boar is said to exceed 12 feet. So that would be R-1 is certainly not small. That's turbulent. And is so terrific in its appearance and dangerous in its consequences that no boat will venture to pass at spring tide. The reason I read this to you is because of what he then says. The Hoogly Boar, as fearsome as it could be, is but a ripple compared to the Kiantang Boar, the greatest of tidal boars. Between the river and the city walls, which are a mile distant, dense suburbs extend several miles along the banks. As the hour of flood tide approached, crowds gathered in the streets, running at right angles with the Kiantang, but at a safe distance. Now, I went to see this, and here it is. So here's Shanghai, and here's Shanghai, and here's Hangzhou. This is 50 kilometers. Here's the river. And the Boar is in this region here when it seriously narrows. We stayed in the hotel. You know, the River Severn is about 50 meters wide. Here, where the Boar happens, it's several kilometers wide. So the scale is much bigger. The height isn't enormously bigger, but it just stretches way across to the horizon. And we saw it half a dozen times, morning and evening, morning and evening, morning and evening. Now, you know, it's mentioned in folklore. President Xi quoted a poem, every year on the 18th day of the 8th month, it isn't precise there, men and women from many hundreds li away gather to see the boatmen and fishers plunge against the boars. Well, it's an entertainment, you know, with people there, people being entertained while they watch, and policemen are there because silly people actually jumped in and were killed, because you can be swept underneath when the boar comes in. So they carefully prevent people coming. When we saw it, there were about 120,000 people estimated to be on the banks. And here are some of them, and here it goes by. And I was slightly above, looking down, and I took this picture. Now, what you don't see, because this goes out of shot, is that the tide comes in and overtops much of this structure. Here it is. Again, it's a turbulent bore. There we are. I won't show you a picture I took at night, although I just must say that I like to go and see the boar at night. It's actually even more impressive than during the day, and that's because you can hear it much better because of the way sound refracts in temperature gradients. So you hear things at night more clearly from a distance than you do in the day, and you hear it coming before you see it sometimes. Something I've never seen anywhere else, I want to show you. So here it is coming in. You see the sort of faint residue of the waves I've been describing, but it's essentially a turbulent bore. I want you to see the scale. You see, they lift these boats up to keep them out of the way, but look at the people, how small they are. So you see the scale. Now here's something I haven't seen described or seen anywhere else. You see, the bore comes in, and there's a part of the river where you get this, this wall poking out, and the bore hits it. And of course, when it hits it, you get a reflected bore. I have seen this very faintly in the Severn bore when the river hits the weir at Maysmore. You have to wait from the bridge where you see it. You have to wait about a few minutes, and then you can, if you're lucky, we've seen it once. But this I want to show you. So here's the advancing bore. There it is. Now, here it's coming in. I'm standing on this wall, watching it approaching. And it hits the bore, then it recedes, and it interferes with its reflection and goes away. So it's quite a dramatic, nice thing. Now, the River Seine at Caudebec used to be a place where you could see the bore. You can't now because they dredge the bottom, and that spoils the condition. So you see some waves, but not really a bore. But there were famous pictures. Here are some. But I say not now. And I saw this picture when I was a teenager. I was interested in astronomy, and there's a beautiful French book on astronomy by Flammarion and Gore. Flammarion is the author and Gore was a translator, and that's where I first heard of the bore. And I saw this picture, which is, I think, fanciful, but it's nevertheless very beautiful, and you do see some of the waves. It's different from what I think they really would have looked like, but still it's quite dramatic, and I was very impressed by it. And I'm going to finish by reading what is quoted there. One day, after being present at Caudebec, after this always curious spectacle of the bore of the Seine, I returned on foot, where I was overtaken by a countryman with whom I entered into conversation. On my asking him what he thought, and what the old people of his family thought of the phenomenon which they had observed for so many years, I do not know, he replied, how the wise men explain it, but for us it seems to be nothing else than the well-known antipathy between salt water and fresh, They are not of the same character, you see. But this is certain, that the fresh water falling into the sea worries the salt water with which it finds a difficulty in mixing. Well then, the salt water ends by becoming angry. It accumulates its anger, and every evening, especially at the equinoxes, when it's already naturally furious, it resolves on hunting the fresh water and sending it back with great velocity. Then he continues, I assure you, sir, that this reason is much simpler than the attraction of the moon. Now, I don't disparage this because you need to know quite a lot of physics to understand what's happening as I've described. And it's very natural that if you're not a scientist, but you're a thoughtful person, you think, well, what possibly could it be? And it's a wrong theory that the salt water and the fresh water oppose each other, but it's not stupid. But I want to read you this as well, which is from Mythology, also from the same book. The Seine, nymph of Ceres and daughter of Bacchus, walking one day on the seashore, was seen by Neptune, old monarch of the waters, who, delighted with her charms, set out to follow her. He had already reached her when Bacchus and Ceres, invoked by the nymph and being unable otherwise to save her, metamorphosed her into an azure river, which ever since has borne her name, and has everywhere on its banks joy and fertility. Neptune, however, has not ceased to love her, although she has preserved her aversion to him. Twice a day he pursues her with great bellowing. Unfortunately, sexual harassment is not a new phenomenon. Twice a day he pursues her with great bellowings, and each time the Seine escapes into the meadows and goes back towards its course, contrary to the natural course of rivers. Whoops. So here's how I like to describe it, I mean, in fundamental terms, because it illustrates something very beautiful. You see, what do we try to do in physics at the deepest level? We want to unify. You know, Maxwell, our technological civilization is based on Maxwell observing that electricity, magnetism, and light are all part of one structure, electromagnetism. We have the electroweak theory, electricity, magnetism, and the weak interactions are unified. The quest among some fundamental physicists now is to unify gravity with these other forces. But the first unification was Newton. And he told us that it's at the very heart of physics, that gravity that holds us down and holds the Earth in its orbit and pulls the tides is all one force. And when you see the Boar, you see the coincidence of those three effects that Newton pointed out to us. There's no evidence that Newton ever knew about the tidal bore or saw anything similar, although there's one near Nottingham, not that far from where he lived, but he never mentioned it. Stop. Thank you.
Can I ask if there are any questions?
Just want to say one thing. I don't hear very well, so I might ask Ted to repeat whatever it is you say. Sometimes it works, sometimes it doesn't. Yeah. Yes. I'll come by, but I can hear you better.
Thank you very much for the lecture. So you mentioned that there is a parameter above which it will be different, turbulent.
Yes.
So is this turbulence connected with nonlinearity, which you try
Oh,
to
sure, I'm sure. Yeah,
suppress?
yeah, linear theory won't work for that. No, that's way out of what I was describing.
Because in hydrodynamics, so you have something linear, then you have laminar flow,
Yeah,
and then you have turbulence.
yeah, sure.
So is there any chance for laminar nonlinear?
I'm sure there is, and there are theories of bores. There's a literature. Going back, actually, to my dear colleague, my late colleague, Hal Peregrine, who's been mentioned already, and I really wish he was alive because I wanted to discuss this with him. I mean, other things we discussed, for example, caustics and caustics in waterways, which he was looking at a non-linear extension of, many things. But unfortunately, well, he died too young. But yes, there are many formalisms, But as I say, I'm thinking that in this limit I was describing, this very, very large T and so on, this universality emerges. It could be that for much larger version T's, which don't happen for these tidal bores, that the nonlinearity which I've neglected comes in, for example, in KdV, and you would then get a separation of the waves. That's another known nonlinear phenomenon. But in this minimal model, I don't need it. So yeah, of course, there's a literature. Yeah.
Tsunami, and if I remember, Yefim Pelinovsky, whom you mentioned regarding tsunami, probably you, sorry, he said he answered the question: is tsunami linear wave or non-linear?
Oh no,
it's a 50,
no,
it could be linear, it could be non-linear.
Depends where. No, right. With a tsunami, it's certainly non-linear where it's created. It's certainly non-linear when it runs up the shore. But in between, it's linear. I mean, the ocean depth is kilometers, and the height is a few tens of centimeters, and the wavelength is kilometers, is many, sorry, tens or hundreds of meters. So it's absolutely the regime of linear wave described. And when people make the maps of the tsunamis, how they travel based on the measured depths of the oceans, or these tsunami atlases, they just consider the front, and they use root GH, where H is the depth. So H is like a refractive index, and within linear wave theory, something you can do, which I understood, is that if you have variations of the depth, which you do have, particularly underwater islands in particular, they can act like focusing lenses, and you get focusing. And this means that the heights of when they reach the shore can be very different from what's predicted if you don't include these focusings. And I have to say, I was very nervous when I submitted this paper about focused tsunami waves, but I had very nice reviews, because if you look at the tide map, they give you the first return, the first arrival, because there are several arrivals if you have caustics. But and the maps of the first arrival curves have a finite angle of intersection, they have a discontinuity of slope. And they had never realized that that's due to caustics and to underwater focusing. It's very interesting. But once you see that, you know where the tsunami is going to be large when it's non-linear, when it reaches. So yeah, but in between you can get a lot from linear theory. And in particular, I used the uniform approximation. So it's not just near the front, which you can see in Jeffries and Jeffries. I mean, long ago, they wrote this in the whenever it was, 30s or 40s. But you can stretch that Airy function, so it gives an accurate description everywhere. Yeah. But the point about the Boar is, because it's an integral of it. That's the distinctive feature. There was a question somewhere. Oh, yes, Silke. I'm going to come so I have a chance to hear you.
Okay, I will speak very loud.
Yes?
Okay. So first, it was a very nice presentation. Thank you. I have just a couple of thoughts about it.
Yes.
The first one is, there are no transverse waves to it, which would be a very clear sign of nonlinearity. Sometimes you can get transverse modes in a system, and that.
Yeah, I mean, of course, you get little ones that come from the shore, but they disappear quickly as you get near the middle. That's different.
No, but that is because the riverbed is.
Yeah,
changing.
exactly.
So that is not.
I know, I understand. Yes.
But you don't get wave trains transverse.
No.
So that's a good sign. If I look at the pictures, I would say, well, you see that the troughs and the heights and the wave seems to have some cubic terms or something in it, because it does seem a bit.
Yeah.
But I was wondering.
It varies a lot between different bores. I mean, the one I showed you, it doesn't happen with the one I showed you with that video. It doesn't. It's not there. But yeah.
I mean, one of the things is, if you do have nonlinearities, and it's sort of a self-interaction.
Yes.
All it would do, it would give you a nonlinear damping,
Yes.
which you couldn't see. You would just register it as more damping. And you could get a shift in the frequency. And so in a way, it just changes, it redefines your mean flow.
Yeah. Do you mean damping caused by viscosity, or damping caused by waves traveling, taking away the energy?
Amplitude. The fact that this one amplitude is very high.
Yes, but
then a non-linear damping term.
But damping, you don't mean dissipation from viscosity, because that's probably negligible.
That's negligible. It's
Yeah.
a non-linear damping caused by the wave amplitude itself. So you can
Yes,
get
but why is it damping if you have no viscosity?
because if you look at the equation, the wave equation, it's sort of, there's a linear damping term which is small, plus it would enter in the same, it is.
No, but damping is a loss of energy. So you're talking about energy that's taken away by the waves
Yes.
rather than energy that's taken away by viscosity. I mean, if you neglect viscosity, which you more or less do, this goes for tens of miles without much change, then, then the damping of that kind is not there. So you're using a term in a way I don't understand.
Should we perhaps leave the discussion till over the glass of wine? Which is
Good
right
idea.
outside?
Good idea. Yeah.
and,
So apologies
Can
for
I
not
ask you all
understanding
to
you.
join me in thanking Professor Berry for a fascinating talk?
Yeah. Yeah.